Prove that line voltage equals to root 3 times of phase voltage and line current equals to phase current in a star connection. This is diagrammatic view of a star connection where VR, VB and VY are the phase voltages, VRY, VBR, VYB are the line voltages, and IR, IY, IB are the line currents. This is a phasor diagram for star connection where each phase is having a phase difference of 120 degrees. So V by V are having a difference of 120 degrees, then VR and minus VY will be having a 60 degrees apart. This is a semi-circle where total angle is 180 degrees. So the line voltages are 120 degrees apart from each other, as well as the phase voltages are also 120 degrees apart to each other. The line voltages are 30 degrees ahead of their respective phase voltages. We can observe from this phasor diagram. Let VR equals to Vy equals to Vb are the phase voltages. Similarly, Vry equals to Vyb equals to Vbr are the line voltages. We need to find out the relation between the line voltages and the phase voltages. Now consider Vry is equals to vector difference of Vr and Vy, or else we can write this as Vr minus Vy. Squaring on both sides, then we will be getting Vry equals to square root of Vr square plus Vy square plus 2 Vr Vy, and the angle between these two between Vr and Vy is 120 degrees, but here we have considered the minus Vy, so I'm replacing the Vy with minus Vy. Then the angle between Vr and minus Vy will be 60 degrees, so cos of 60 degrees. Replace this Vr with the V phase, so square root of V phase square plus, this is also V phase square plus 2 times of Vr and Vy is also V phase square. Cos 60 is 1 by 2. That equals to square root of 3 V phase square. That equals to root 3 times of V phase. So Vry is nothing but the line current. We can write VL equals to root 3 times of V phase. Hence it's proved. And you can try for Vyb, which equals to the phasor sum of Vy minus Vb, and similarly Vbr equals to Vb minus Vr. Now, if you observe, the line current IR is in series with the line phase current, so both are equal in case of a star connection. So hence, in star connection, the line current in each line is the same as the current in the phase winding to which it is connected. IR equals to IY equals to IB, which is a phase current. Then from this it's in series, so we can say that in generalizing IL equals to I phase. So for balanced star connection, IR plus IY plus IB equals to 0. If the Y connection is not balanced, then the current other than this value will flow through the fourth line, that is a neutral line, and given to the grounded. The angle between the line current and the corresponding voltage for a lagging loads, if you observe, then this is the current IR, which will be 30 degrees plus this is the angle phi. So the angle between the line current and the corresponding voltage is 30 plus phi for the lagging loads. If you consider the leading loads, the line current 30 plus phi leading. These are the leading currents and these are the lagging currents. The power in a star connection, the total active power or the real power we can call in a circuit is the sum of individual three-phase powers. So the total power P equals to 3 times the individual phase powers, that is VPH, IPH, cos phi, where phi is the angle between phase voltage and phase current. Then 3 into in terms of line. VPH equals to VL by root 3. So VL by root 3. IPH equals to IL cos phi. Now if you calculate, this is root 3 times VL IL cos phi is the total power of the star connection. This is a real power. The total reactive power Q is given by root 3 times VL IL sin pi. Then the total apparent power or complex power, that is S equals to E plus JQ. Then S equals to root P square plus Q square root 3 times VL IL. This is in volts amps, whereas reactive power in kVAr and real power in kilowatts. These are the relations between line and phase voltages and currents in a star connection, as well as the real, reactive and complex power, which is also known as apparent power in star connection. If this video is useful, please like, share and subscribe.